Welcome to the deep dive. Okay, so today we're diving into C#. We've got this pretty comprehensive tutorial here, really laying out the fundamentals.
That's right. It's all about getting that solid base, understanding the language itself, and the whole .NET world it lives in.
And our mission, as always, is to kind of cut through that, pull out the essentials, and get you up to speed quickly on what C# actually is, how it works, the key pieces.
Exactly.
Yeah.
Because C# is, well, it's a big deal. It's modern, pretty powerful, and you see it everywhere. Desktop apps, web services, even games. Lots of stuff.
So yeah, let's not hang about. Let's unpack how this all fits together.
Okay, so C#, at its core, it's what's called a general-purpose, object-oriented programming language. Microsoft built it.
Right.
And it's actually standardized by ECMBA and ISO, which tells you it's pretty well-defined, robust, built for serious applications. Security is a big focus, too.
And you basically can't mention C# without talking about .NET. The source really hammers this home.
Oh, absolutely. They're intertwined. Your C# code, it needs the .NET platform to run. Think of it .NET as the runtime environment and the library of tools C# uses.
It used to be mainly a Windows thing, but it's broader now.
Yeah, it's cross-platform now.
Yeah.
And it doesn't just run C#. Other languages work with it too. NET itself stands for Network-Enabled Technologies, though. That's kind of historical now.
The source mentions some key .NET parts. CLR, FCL.
Right, key acronyms there. The CLR, Common Language Runtime, that's the actual engine. It executes your code, handles memory management, security checks, all that critical stuff.
Okay, the engine.
Then there's the FCL, Framework Class Library. This thing is huge. It's like a massive pre-built toolbox full of code you could just use.
Saves you writing everything from scratch.
Totally. It's organized into namespaces, like System for Basics, System.Data for databases, System.Web, lots more. Just pull in what you need.
And MSIL, or CIL.
Yes, MSIL or CIL Microsoft, or Common Intermediate Language. It's an intermediate step. Your C# code doesn't compile straight to machine code. It compiles to this IL first.
Why the extra step?
Well, the CLR then takes that IL and compiles it again just in time for the specific machine it's running on. It helps make .NET code portable, runnable on different kinds of hardware or operating systems without needing a total rewrite.
Got it. So C# runs on .NET. To actually write it, the source points to Visual Studio.
Yeah, Visual Studio, that's the main integrated development environment, the IDE for C#. It's your workbench, really. You write code, design interfaces, debug, test, all in one place.
Made by Microsoft too, naturally.
Yep. When you install it, you pick workloads like .NET Desktop development or ASP.NET Web development, which just bundle the specific tools you'll likely need.
And inside VS, you work with solutions and projects.
Right. A solution is just a container, holds one or more related projects. A project is where your actual code, assets, configuration live. For learning, a console application project is perfect. Simple text in, text out.
Keeps things focused on the code itself.
Exactly. The source suggests starting with a blank solution, then adding your project. Good habit for organization.
All right, workbench ready. Let's look at the code. The classic hello world. The source breaks down that basic structure.
Okay, yeah. Your first lines of C# usually starts with using system. That using keyword is everywhere. It tells the compiler you want to use types from the system namespace.
So you don't have to type system.console right line every time.
Precisely. System is fundamental. It has core stuff, like the console class for interacting with the console window.
Makes sense. Then namespace. Your namespace name?
Namespace is for organization, like putting your code files in a labeled folder. If you use two different libraries that happen to have a class named helper, namespaces keep them separate. You'd have library A helper and library B helper. Prevents clashes.
Good practice. And inside that, class program.
Class. This is central to object-oriented programming, or OOP. Think of a class as a blueprint, a template. It defines what kind of data objects made from it will hold and what actions they can perform.
Blueprint for objects. Got it. Then the big one, static void, main string args. Looks important.
It is the entry point. When you run your C# program, the CLR looks for this main method and starts executing there.
Okay. Why static?
Static means the main method belongs to the program class itself, not to a specific instance or object of the class. Which makes sense, right? The program needs a starting point before any objects are even created.
And void just means it doesn't return anything.
Correct. It runs, does its job, and finishes. String args. That's an array of strings. It catches any arguments you might pass to your program from the command line when you launch it.
Like configuration options or something.
Exactly. Maybe a file name to process.
And finally, the actual output. Console.WriteLine hello world.
There it is.
Yeah.
Console is the class, WriteLine is the method. It prints the text hello world to the console and then adds a new line.
There's also console write.
Yeah, write does the same thing but without the new line. And for getting input from the user, you've got methods like console.read or console readline.
So that's your first interaction, getting data in and out.
That's your basic communication channel with the user, yeah.
Okay, structure, printing text. Cool. But programs need data, stuff that changes. How does C# handle different kinds of data?
Right, that's where data types come in. There are keywords like int, string, bool that tell the compiler what sort of data a variable will hold. Is it a whole number? Text. True or false?
And why does the compiler care?
Well, it affects how much memory gets allocated, for one. And it determines what operations you can actually do with that variable. You can add two ints, but you can't really add two bools in the same way.
Makes sense. The source talks a lot about value types versus reference types. That seems important.
It's fundamental. Really crucial distinction in C#. Value types, think int, float, bool, char, also things called structs and enums. They store their data directly in the variable's memory location.
Okay, the data's right there.
Right. And if you assign one value type variable to another, like int b equals a, you get a complete copy of the data. They're independent after that.
Like photocopying a document? What about reference types?
Reference types like string, object arrays, classes, interfaces, delegates, they work differently. The variable holds a memory address, basically a pointer, to where the actual data is stored elsewhere, usually in a memory area called the heap.
So it's just a pointer, not the data itself.
Exactly. So when you assign one reference type variable to another, like my class of JB, of JA, you're only copying the address. Both variables now point to the same object in memory.
So if you change the object using objb, you'll see the change when you look through obj too, because they point to the same thing.
Precisely, like sharing a link to a Google Doc instead of sending a copy. This difference impacts everything, especially how you pass data into methods.
Okay, value types are copies, reference types are shared references. How do you declare them?
Simple syntax. Data type variable name declares it. Data type variable name equals value, declares, and gives it an initial value.
And the source mentioned .get type.
Yeah, that's a method you can call in any variable at runtime to see its actual underlying .NET type, like system.int32 for int or system.string for string. Useful for debugging.
The source lists common types. Int, float, bool, char.
Right. Int for whole numbers, float for decimals, bool for true false, char for single characters inside single quotes, and string for text inside double quotes. Also date time for handling dates and times.
Okay. What about identifiers? Just names for things.
Pretty much. Identifiers are the names you choose for your variables, classes, methods, whatever. There are rules though.
Like?
Got to start with a letter or underscore. Can contain letters, digits, underscores. They are case sensitive, so age are different. Can't be a reserved keyword like class or if. And there's a length limit that's huge, like 512 characters. Just keeps things unambiguous.
And a variable is just that named identifier holding data that can change.
Exactly. It's your named placeholder in memory. You store data, retrieve it, change it. The source mentions you can initialize it right in the code compile time initialization like int_score 0 log. Yeah. Or get the value when the program runs, maybe from the user typing something in runtime initialization using console readline.
What if you need to store like a list of scores, not just one?
That's exactly what arrays are for. Arrays let you store multiple values, but they must all be of the same data type, under a single variable name.
And there are reference types, you said?
Yes, arrays are reference types. A big advantage is that their elements are stored contiguously, right next to each other in memory, which makes accessing them really fast.
How do you get a specific score out of the list?
Using an index. And critically, array indices start at 0. So the first element is at index 0, the second at index 1, and so on. You declare an array like data type array name, and then you initialize it, usually specifying the size, like array name, you get a type 10, to create an array that can hold 10 items.
The source mentioned different kinds of arrays too.
Yeah. The basic one is a one-dimensional array, just a simple list. But you can have multi-dimensional arrays, like a 2D array, which is like a grid or table thing, rows and columns, or even 3D.
Rows and columns. Useful for games or spreadsheets.
Definitely. And then there are jagged arrays. These are a bit different. They're arrays of arrays. The inner arrays don't all have to be the same length.
Okay, a bit more flexible. How do you work with, say, a 2D array?
Often with nested loops. You'd have one loop for the rows and an inner loop for the columns to access each cell, like my grid row, column.
Right. So arrays, efficient way to handle collections of the same kind of data. Makes sense.
Fundamental data structure, really.
Okay, we've got data, ways to store it. How do we actually operate on that data and control which code runs?
Operators and control flow statements. That's the next big piece. Operators are symbols that perform operations. Think plus L8.
Basic math.
Exactly. Those are arithmetic operators. Percent is the modulus operator, gives you the remainder of a division. Super handy.
Remainder. Like four-teching even or odd?
Perfect example. Number percent 2. If it's 0, the number's even. Then you have relational operators for comparisons.
Yeah.
And for equality, it's double equals important distinction.
Yeah.
And for not equal.
Comparisons are key for making decisions later, I bet.
Absolutely. Assignment operators put values into variables, this is the basic one, but there are shortcuts like plus a equals 5 is just shorter than writing x equals x plus 5.
It's convenient. What about unary operators? Plus, and go.
Those operate on just one thing, plus increments a number by 1, decrements it by 1. The source highlights the difference between pre-increment plus I and post-increment I plus plus.
Oh, yes, the tricky bit.
It can be. Plus I increments first, then uses the new value. I plus plus uses the current value, then increments after. The timing matters depending on how you use it in an expression.
Okay, watch out for that one. So operators do the work, control statements direct the flow.
Exactly. They let your program make choices, repeat blocks of code, or jump around based on conditions. Two main kinds. Decision-making and looping.
Decision-making, the if statement.
That's the main one. If condition runs the code block, only if the condition is true. Add an else block for what to do if it's false. Use else if to chain multiple conditions together. If this, else if that, else if something else.
You can nest them too. An if inside an if.
Yep, nested ifs for more complex logic. And then there's the switch statement.
When would you use switch instead of a bunch of if-else ifs?
Switch is often cleaner when you have one variable or expression you want to compare against several specific constant values, like checking the value of a day of week variable against Monday, Tuesday, Wednesday, etc.
Specific values.
Right. The case labels must be constants, like numbers or string literals, no duplicates allowed. And you usually need a break statement at the end of each case block to exit the switch. Otherwise, execution falls through to the next case, which you usually don't want. There's an optional default case for anything that doesn't match the other cases.
Okay, that's deciding. What about repeating code, looping?
3 main loops. The while loop checks its condition before each iteration. If it's true, it runs the loop body. If false, it stops. It might not run at all if the condition is false the first time.
What if you need it to run at least once?
That's the do while loop. It runs the loop body first, then checks the condition after. So it always executes at least one time.
And the for loop? Seems common.
Very common, especially when you know roughly how many times you want to loop, or you have a clear counter. The for loop structure neatly combines 3 parts. Initialization runs once at the start, like int I equals 0. The condition, checked before each loop, like I10. And the iteration step runs after each loop, like I plus plus.
Very structured.
Exactly. And like ifs, you can have nested for loops, a loop inside a loop. Super common for working with those 2D arrays, iterating through rows and columns. Just be careful not to create an infinite loop where the condition never becomes false.
Yeah, that sounds bad. The source also mentioned jump statements.
Yeah, these change the flow more abruptly. Break immediately jumps out of the current loop, for, while, do while, or switch statement.
Gets you out completely.
Right, continues different. It skips the rest of the current iteration of the loop and jumps straight back to the condition check for the next iteration.
Skips one iteration, basically.
Or the rest of that iteration, yeah. Go-to jumps directly to a labeled statement elsewhere in the method. Use this one very carefully, if at all. It can make code really hard to read and debug.
Okay, warning noted.
Return exits the current method. If the method has a return type other than void, return also sends a value back to the caller. And throw is used to signal that an error has occurred by creating and raising an exception.
Okay, that's a whole toolkit for controlling execution. Now let's get back to that object-oriented stuff, classes and objects.
Right. C# is built around OOP. We said a class is like a blueprint. It defines the data, attributes or fields, and the actions methods that objects of that type will have in common.
And an object is an actual thing created from that blueprint.
Exactly. If car is the class blueprint, then a specific red Toyota parked outside is an instance or an object of the car class.
Yeah.
As state, color is red, make is Toyota. And behavior, it can start engine, accelerate.
Can you make one of these objects?
Using the new keyword, like car my car easily new car. That creates a new car object in memory, and the mycar variable now holds the reference to it.
And you access its properties or call its methods with the .myCarColor myCarStartEngine.
Precisely. Dot notation. Now, when you write new car, something important happens behind the scenes. A constructor is called.
Constructors. Okay, what are those?
They're special methods inside the class. They have the exact same name as the class, and importantly, no return type, not even void. Their whole job is to initialize a new object when it's created, set up its initial state.
So they run automatically with new.
Yep, every class has at least one. If you don't write one yourself, C# provides a default parameterless one that does basic initialization, like setting numbers to 0, objects to null.
But you can write your own.
Oh yeah, a parameterized constructor takes arguments, so you can provide initial values right when you create the object. Car, my car, new car, red, Toyota. Makes setup cleaner.
The source mentioned other types too. Private, static.
Right. A private constructor can only be called from within the class itself. This is often used in patterns like the singleton pattern, where you strictly control object creation, maybe ensuring only one instance ever exists.
Okay, advanced usage. Static.
Static constructors are weird. There's only one per class, no access modifiers, no parameters. It runs automatically just once. The very first time the class is used in any way, like accessing a static member or creating an instance, its job is to initialize any static fields of the class.
And copy constructors.
A copy constructor takes an existing object of the same class as a parameter and initializes the new object using the values from the existing one. A way to clone an object, basically.
So constructors handle the birth and initial setup of objects. What about controlling who can access the parts of an object once it exists?
Access modifiers. These keywords, public, private, etc., control the visibility or accessibility of your classes and their members. Fields, methods. This is key to encapsulation.
Encapsulation. Bundling data and methods together.
Exactly, and protecting the internal data. You decide what parts of your class are exposed to the outside world and what parts are internal implementation details.
So public, private are the main ones.
They're the most common. Public means accessible from anywhere. Private means only accessible from within the same class. This is your default for protecting internal data.
What about protected and internal?
Protected means accessible within the defining class, and in any class that inherits from it, derived classes. Internal means accessible anywhere within the same assembly. Think of an assembly as your compiled project output, like a .dll or .exe file.
Okay, so internal is about project boundaries. The source had combinations too.
Yeah, they get a bit more specific. Private protected means accessible within the class and derived classes, but only if those derived classes are in the same assembly. Protected internal is the most permissive. Besides public, it's accessible within the current assembly, or R and derived classes, even if they're in a different assembly.
And there are defaults if you don't specify.
Yes. For top-level types, like classes declared directly in a namespace, the default is internal. For members inside a class, fields, methods, the default is private.
Why bother with all this? Why not just make everything public and easy?
But that breaks encapsulation. Think of it like building a TV. You don't expose all the internal circuit boards and wires, private members. You provide a controlled interface to remote control with buttons, public methods like change channel, adjust volume. This protects the complex internals from being messed up accidentally and makes the TV easier and safer to use. Access modifiers enforce that boundary.
So it's about protecting the object's internal state and providing a clear, safe way to interact.
Exactly. Prevents accidental corruption, makes code easier to maintain because you know where changes can come from.
Okay, that makes more sense. The remote control analogy helps. So let's build on this OOP foundation. Methods in more detail. Inheritance, polymorphism.
Right. We know methods are blocks of code doing specific tasks inside classes. Big benefit, that code reuse. Write it once, call it many times.
And the declaration involves access modifier, return type, name, parameters.
Yep, and calling or invoking the method just runs that code. Now, those parameters, the input, the source digs into how data gets passed. The default is by value.
Meaning a copy is passed.
Exactly. For value types, int, struct, a copy of the value goes into the method. For reference types, class objects, a copy of the reference, the address, goes in. In either case, if you reassign the parameter variable itself inside the method, it doesn't affect the original variable outside.
But you can change that with ref and out.
Correct. The ref keyword means you're passing the variable by reference. No copy is made. The method parameter becomes an alias for the original variable outside. Any changes to the parameter inside the method directly affect the original. Crucially, the variable must be assigned a value before you pass it using ref.
Okay, direct link. What about out?
Out is also passed by reference, so changes affect the original. The key differences are, the variable passed with out doesn't need to be initialized beforehand, and the method must assign a value to the out parameter before it returns. It's often used when a method needs to effectively return multiple values.
So ref is for data going in and potentially out. Out is purely for data coming out.
That's a good way to think about it. Then there's params.
Param.
The params keyword lets you define a method that can accept a variable number of arguments of a specific type, like a sum method that could take sum 1, 2, or sum 1, 2, 3, 4, 5. Inside the method, those arguments arrive as an array.
Handy. And default optional parameters.
Let you specify a default value in the method declaration, like void do something, in value with 10. If the caller doesn't provide an argument for value, it automatically gets 10. Makes methods more flexible. Dynamic parameters are more specialized, deferring type checking, mainly for interacting with dynamic languages or COM objects.
Okay, lots of ways to handle method parameters. Next big OOP pillar, inheritance.
Inheritance. This is where you create a new class, derived or subclass, that gets features from an existing class, base or superclass. It's all about is-a relationships, a dog is an animal, and code reuse.
How do you show that relationship in code?
With a colon. Dog animal. This is the dog class inherits from the animal class. Dog automatically gets all the non-private members, fields, methods of animal.
The source mentioned different patterns, single, multi-level.
Yeah. Single inheritance is one base class. Multi-level is a chain. C inherits from B, B inherits from A. Hierarchical is one base class with several different derived classes branching off it.
What about multiple inheritance, inheriting from two different base classes?
C# does not allow a class to inherit directly from more than one class. That can lead to ambiguity, the diamond problem. However, C# does allow a class to implement multiple interfaces, which is how you achieve similar goals, inheriting multiple contracts or sets of capabilities.
Okay, no multiple class inheritance, but multiple interface implementation.
Got it.
And hybrid is just mixing these patterns. And so inheritance is building on existing blueprints. Polymorphism, many forms.
Literally many forms. It's the idea that something, usually a method call, can behave differently depending on the context. Two main types: static at compile time and dynamic at runtime.
Static is overloading.
Yes, method overloading. This is when you have multiple methods in the same class with the same name but different parameter lists, different number, type, or order of parameters. The compiler figures out which version to call based on the arguments you provide when you call the method. Return type alone doesn't count for overloading.
Same name, different signature, same class.
Perfect summary. Dynamic polymorphism is method overriding.
This involves inheritance, right?
Yes. Overriding is when a derived class provides its own specific implementation of a method that is already defined in its base class. The method must have the exact same name and same signature in both the base and derived class.
How does the system know which one to use?
You need keywords. In the base class, you mark the method with virtual to indicate the derived classes are allowed to override it. In the derived class, you use the override keyword to signal that you are providing a new version. The actual method called depends on the runtime type of the object, not just the type of the variable holding it. So virtual in base, override in derived. Same name, same signature, different class, base versus derived. That's the key difference from overloading.
Absolutely crucial distinction. The source also mentions operator overloading, letting you define how operators like plus AA
Work with your own custom class types using the operator keyword. Okay, core OOP covered. What other powerful features did the source highlight? Input-output, file handling. Right. Beyond the console, you often need to read from or write to files. The system.io namespace is where you find the tools for this. It works with the concept of streams.
Streams, like a flow of data.
Exactly, a sequence of bytes. Data flows from a source, file, network, memory, through the stream to your program, or from your program through the stream to a destination. Console.io uses streams too, under the hood.
So file handling uses streams.
Yes. You open a file, and you get a stream connected to it. The source mentions StreamReader and StreamWriter as convenient classes for working specifically with text files. For more general byte-level file access, or more control over how the file is opened, read-only, write, append, etc., you'd use FileStream.
And the file class.
That provides static helper methods for common file operations without needing to explicitly manage streams sometimes. Things like file.exists, filepath, file.copy, file.readAllText. Quick shortcuts.
Next up, generics. Sounds flexible.
Extremely flexible. Generics let you write code classes, methods, interfaces that can operate on data of any type without committing to a specific type when you write the code. You use a placeholder, usually T.
Like a template.
Very much like templates in C++O.
Yeah.
When you use the generic code, you specify the actual type you want to use for T, like liststring or listen.
What's the advantage?
Several big ones. Type safety. The compiler knows you intend to use, say, a list of strings, so it prevents you from accidentally adding an integer. You catch errors at compile time, not runtime. Code reuse. You write the generic listy logic once, and it works for strings, ints, customers, anything. Performance. Especially with collections of value types, generics avoid performance overhead associated with older, non-generic collections that had to treat everything as a generic object.
So safer, reusable, faster code. Where do you see them most?
Collections are the prime example. System.collections. Generic has things like list, dictionary, t-key, t-value, qadd, stack t. You use these all the time. You can also write your own generic methods or classes.
Okay. The source also covered struct, interface, and enum. More ways to define types.
Yeah, user-defined types beyond classes. A struct is defined with the struct keyword, the absolute key thing to remember. Structs are value types, unlike classes which are reference types.
So they behave like interbool regarding copying.
Exactly. They're typically used for small, lightweight data containers, like representing a point with x and y coordinates, or maybe an RGB color value. They can have fields, methods, constructors, but their value type semantics are the main differentiator.
And interface, we touched on this with inheritance. It's a contract.
Precisely. An interface defines a contract. It lists method signatures, property definitions, events, indexers that a class must implement if it claims to implement that interface. It usually doesn't provide the actual implementation code itself, though default implementations are possible now.
And classes implement interfaces.
Yes, a class can implement multiple interfaces. This is how C# gets around the lack of multiple class inheritance. A class can inherit the implementation from one base class, but it can inherit the contracts, what it must do, from many interfaces. Uses the interface keyword to define, and a colon for a class to implement it.
Okay. And enum, enumerations.
Enums provide a way to create a set of named constants, usually related to integers. Think enum status, pending, processing, completed, failed. Underneath, these names usually map to integers, 0, 1, 2, 3 by default. But using the names makes your code much more readable and self-explanatory than using magic numbers.
So instead of checking if order status equals 2, you write if order status dot completed.
Exactly. Much clearer, less error-prone. You define them with the enum keyword. You can explicitly set the underlying integer values if needed, and you can cast between the enum type and its underlying integer type.
Okay, struct, interface, enum, useful additions to classes. We're nearing the end. The source covered delegates, events, and some expression types.
Right, these are often used for connecting different parts of an application or writing more concise code. Delegates can be a bit mind-bending at first. Essentially, a delegate is a type that represents a reference to a method.
A variable that holds a method.
Kind of, yeah. It's like a type-safe function pointer. You define a delegate type that specifies a method signature, return type, and parameter types. Then you can create instances of that delegate that point to actual methods matching that signature.
Why would you do that?
Key use cases are event handling and callbacks. For events, one object needs to notify others when something happens. Delegates provide the mechanism for subscribers to register their what to do when it happens methods. For callbacks, you might pass a delegate pointing to your method into another method, so that method can call back into your code when it's done or needs something.
Can a delegate point to more than one method?
Yes, that's called a multicast delegate. You can use plus to chain methods together onto a single delegate instance and to remove them. When you invoke the delegate, all the chain methods are called in order.
Okay, delegates point to methods. Events use delegate.
Exactly. An event is basically a controlled way for a class, the publisher, to expose a delegate, allowing other classes, subscribers, to attach their event handler methods, which must match the delegate's signature. The publisher can then raise the event, which causes the underlying delegate to invoke all the subscribed handlers. It provides a standard, safe pattern for notifications, declared using the event keyword.
So events are like managed delegates for notifications. What about anonymous types, methods, lambdas?
These are all about writing code more concisely, often inline. Anonymous types let you create simple data holding objects on the fly without formally defining a class. You just use new property name value, another property value too. The compiler infers the type, Properties are read-only, useful for temporary data structures, maybe in LINQ queries.
Anonymous methods.
An older way to create an inline block of code that can be assigned to a delegate variable using the delegate keyword directly. My delegate type, my del delegate in text. Return my 2. You avoid creating a separate named method just for this delegate.
And lambda expressions.
Lambdas are the modern, much more concise syntax for anonymous methods. They use the operator read as goes to. So that previous example becomes my delegate type, my del x by 2. The compiler often infers the parameter types. X is inferred as int here. Lambdas are used everywhere with delegates, events, and especially LINQ. They make code much shorter and often clearer once you're used to them. Wow, okay. That was a serious deep dive through C# fundamentals.
Yeah, we covered a fair bit. From the absolute basics what C# is, the .NET ecosystem, setting up Visual Studio through the core language elements like types, variables, operators, control flow.
Then the whole object-oriented side. Classes, objects, constructors, access modifiers, inheritance, polymorphism.
Right, and then some of the more powerful tools like file I/O, the flexibility of generics, other type definitions like structs and interfaces, and finally the connection mechanisms like delegates, events, and the concise Lambda syntax.
So pulling all that from the source material, you should now have a really solid grasp of those foundational pieces, how they relate, what they're for, like you said, the map and compass.
It really should provide that grounding, whether you're just starting out, needing a refresher, or just trying to understand what C# is all about.
Definitely. So here's a final thought to leave you with. C# and .NET are constantly evolving. We've covered the fundamentals here, but given this foundation, what other areas of this huge ecosystem, maybe asynchronous programming, LINQ in more depth, web frameworks like ASP.NET Core, game development with Unity, what possibilities could exploring those unlock for the kinds of applications you might build next?